So my project is on the engineering of a more efficient SWIR Schottky photodetector through the implementation of transition metals. I know this may seem a little bit unfamiliar and daunting, as there are some rather large words in the title, so I'll break it down for you a little bit. So firstly, what is a photodetector? A photodetector is a small device that can fit on the tip of your finger that is usually silicon-based. Silicon semiconductor properties lend itself to photovoltaic effects. Secondly, what is Schottky? A Schottky junction is a particular type of junction that is commonly used in photovoltaic devices. To illustrate what a Schottky junction is, I'd first have to go through the photovoltaic effect. The photovoltaic effect in the case of a regular PN junction, which is basically two silicon wafers that are bonded together at a junction, one being more positively charged and one being more negatively charged due to the electrons bonded within the crystalline structure. So when light hits this device, electrons will get enough energy to break free from its atoms and cross the junction. Once it crosses the junction, it creates a positive and negative charge on the opposite sides of the junction. When they're connected with a wire or any other type of metal or conductor, it creates an electrical current. Schottky junctions are characterized by the opposite sides being metal and silicon rather than positively and negatively charged silicon on both sides. This lends itself to a few advantages and disadvantages. It is much cheaper and simpler to manufacture, and it also requires a lower activation energy from light to move the electrons. However, it is currently inefficient because it has low hot carrier generation rates and a slow rise time. This means that there are less spots for the electrons to fill once it crosses the junction, as well as a really slow reaction time between the time the light hits the surface of the silicon and when the electron crosses the junction. This is about 15 microseconds, which may seem very slow, or may seem very fast, but is actually really slow in certain applications. Secondly, what does SWIR mean? SWIR is short for shortwave infrared radiation. Its wavelength is on the shorter end of the infrared spectrum, ranging from 0.7 to 2.5 micrometers. It is invisible to the naked eye, which lends itself to many applications in our modern world. One commonly known is thermal imaging. Another common application we see in our daily lives is facial detection. So this project was funded by the Army. The Army has many applications for a shortwave infrared photodetector in its missile defense systems, reconnaissance such as night vision goggles, and communication. The objective of our team at the nanofabrication facility at LSU is to make this photodetector cheaper, simpler, and easier to manufacture. This lends itself to easy mass production, which is suitable for the Army. However, we also need to maintain its high performance and effectiveness. We define effectiveness by the the maximization of the output of electrical current for the same input of light. We wanted to achieve this through the use of transition metals, more specifically aluminum or gold palladium. This is more commonly known as white gold, which you may find in your jewelry. Gold palladium eliminates the disadvantages of Schottky junctions by raising the hot carrier generation rates and speeding up the rise time. The rise time after implementing transition metals can reach about 0.01 nanoseconds, which is 6 degrees of magnitude faster than previous Schottky detectors. So the functionality that we plan to have for this detector is as follows. We wanted light to enter the device and electrons to be freed from its atoms and across the junction. This creates opposite charges on both sides of this junction, and when it's connected, electron current can flow. So the procedure of making this efficient photodetector involves many steps of testing each individual part for max efficiency. This includes deposition of transition metals through the use of a plasma depositor, the deposition of ohmic contacts using aluminum, and electron beam depositors, as well as the removal of certain substances using a plasma asher, and silicon positive doping. One specific element I would like to focus on is KOH etching. It is simple yet integral to the functionality of the device. So what is KOH etching? First of all, KOH is a strong base, more commonly known as potassium hydroxide. When mixed in a solution with IPA and deionized water and a little bit of heat, it undergoes a chemical reaction with the surface of silicon, etching tiny pyramids into the surface of the silicon. So why is this important? Well, silicon is a naturally reflective substance. And in a device that we want to maximize the light entering the device, a reflective surface is not optimal. On the left, you could see a picture of the pyramids taken by a electron microscope. Silicon naturally has a reflectance of about 37 to 40%. With a little bit of KOH etching, it could reach around 12 to 20%. So another way to visualize how KOH etching works is through a chance process. So when photons hit the surface of KOH etched silicon, it has a chance of being absorbed into the material or reflected. If it is reflected off the surface, it has another opportunity to be absorbed. In a real life case, it has more than just two opportunities to be absorbed into the surface. So in our KOH etching recipe, we wanted to find the most efficient and most effective recipe that resulted in the lowest reflectance. So we tested a multitude of recipes found in scientific journals that have been published. So the best recipe that has been published reaches about a 12 to 13% reflectance, which is good, but not exactly where we want it to be. So in the spirit of trying to maximize our efficiency, I decided to come up with my own recipes. My own recipes resulted in a reflectance of around 10 to 11% reflectance. While it may seem as just a 1 to 3% decrease in reflectance, it is really about a 10% improvement, which is huge. With the addition of certain films, this can reduce the reflectance to about 1 to 2%. So the findings in this project can be used in many ways. First being the Army in its many applications such as missile defense and in night vision goggles, but it can also worm its way into your daily lives. It can improve the cost efficiency as well as the effectiveness of your TV remotes. This remote I'm holding in my hand, and even the facial recognition software in your iPhones. It can also find its way into the photovoltaic industry with applications in photodetectors of other wavelengths, as well as solar cells or solar panels, which may just be the energy of our future. Thank you.